Welcome back to Chemistry with Mrs. Miller at BVISD. Right now we're going to be looking at using moles. So what we want to be able to do is predict the quantities of reactants and products in chemical reactions, determine the mole ratios for formulas for compounds, and identify the formulas of compounds by using mass ratios. So the vocabulary that we need to be on the lookout for is molar volume. So in a gas, it's the volume that a mole of gas occupies at STP. Remember, standard temperature and pressure. Temperature being 273 degrees Kelvin, pressure being 1 atm. I'll let you do the other conversions. So the ideal gas law, which is PV equals nRT. We've dealt with that a little bit before, which is pressure times volume equals number of moles times the constant times temperature. Now, we also need to look at the empirical formula. Now, this is a formula of a compound having the smallest whole ratio of number of atoms in a compound. So we dealt a little bit with that in biology, where we looked at different types of carbohydrates. So we know that carbohydrates have a 1-to-1 ratio. So now we're going to go back and look at that. That would be an empirical formula. So we're going to go back and look at that a little bit later. Now, let's do some reviewing, and this is my little time machine. So we're going to click on my little time machine, which is the equation balancing. So we have to review this balancing of equations. And the reason we have to do this is because equations can be balanced in moles or in grams. So we need to look at this. So let's start with some simple ones. We have iron plus oxygen molecule yields Fe3O4. So how do we do that? Well, 3 iron plus 2 O2 yields Fe3O4. Completely balanced equation. Now we have xenon plus fluoride 2, and we have xenon 1, fluorine 6, equals Xe plus 3Fe, and that yields us the same, I'm sorry, it says Fe, but it's F2. All right? So now we have aluminum plus H2SO4 aqueous solution yields aluminum sulfide aqueous solution plus H2. That becomes a little bit harder, but let's go back and look at that. Remember, we can see this as one unit. That's just one thing. We don't have to break that apart. And that will yield us 2AlS plus 3H2SO4 aqueous solution plus aluminum 2SO4 3 aqueous plus 3H2 gas. So I need you, here is the correct answer. I don't have a problem giving it to you, but what I want you to do is go back and work it out in your listening check journal. Okay, so we've already gotten back here, but we have a new time machine that we need to go and look at, and that's the moles and equations. Molecules and equations. Okay, since we can use moles to represent quantities in an equation, we need to remember that we have to be able to practice predicting these. So now we're looking at this equation, N2 plus 3H2. Well, that yields 2 ammonium. Now, we can relate these in moles. That's 1 mole of nitrogen to 3 moles of hydrogen molecules, yielding 2 moles of that compound. So we need to look at them, but we have them in grams. We know the grams, so we have to go back and look at these. Okay? Now, how many grams of hydrogen are going to react with 3.75 grams of nitrogen gas to completely react? So we have to do that special verb analyze. So hydrogen, the amount of hydrogen is completely dependent upon the amount of nitrogen because we have 3-to-1 ratio. So if we have 100, then we need of nitrogen, we need 300 of hydrogen molecules. So the hydrogen is completely dependent upon that nitrogen because of that ratio. It's a 1-to-3 ratio. All right? So first thing we have to do is find the number of moles of nitrogen molecules. So what's the molar mass of nitrogen? Well, we go to our handy-dandy periodic table, and we find out that that is 28 grams. So we have 3.75 grams of nitrogen times that conversion factor, that 1 mole to 28 grams, and then we have another conversion factor, because here, this is our ratio. That's the 3-to-1 ratio that we're looking for. So, apologize. So we have that final conversion that we need to do because we started out in grams of nitrogen, but we want to know grams of hydrogen. So we need to go and do that. So we have that 3.75 grams. We have that conversion factor from grams to moles. Now we have that ratio, mole to mole. And now we need to add that conversion factor for the hydrogen. So we know that 1 mole of hydrogen is 2 grams. Now we just have to work out the math. 0.804 grams of hydrogen. Because all we did was to take 3.75 times 1 times 3 times 2 and divide that whole thing by the quantity of 28 times 1 times 1. Okay, so we can predict the mass of a product in the same way. So if we wanted to know how much ammonium was formed from that same 3.75 grams of nitrogen, and how would we do that? Well, the equation is balanced, so that's a pretty easy deal. So we have this 3.75 grams of nitrogen, 2 times 1 molecule of N2 times 12 moles of NH3 times 17 divided by the quantity 28 times 1 times 1, 4.5 grams of ammonia. Okay, so you have some practice problems that you need to put in your listening check journal. This is the combustion of propane, C3H8. So it produces carbon dioxide and water vapor. What is the mass of carbon dioxide formed when 95.6 grams of propane burns? This is a listening check, so please remember that you might need to go back and view this wonderful piece here. Because remember, you're going to have to balance. I did not give you the equation. You're going to have to balance the whole thing out. Okay, one more listening check. You have a solid xenon hexafluoride, XeF6. So it's prepared by allowing the xenon gas and fluorine gas to react normally. So if we have 10 grams of that xenon hexafluoride, how many grams of fluorine are used? One more listening check. Okay, let's move on to molar volumes and stoichiometric problems. It's time to review again. What's Avogadro's principle? Equal volumes of gases contain equal number of particles at same pressure and temperature. So this can be related in moles as well. We're not really worried about that. We know that they have equal numbers. So molar volume of a gas is related to, or is always taken at STP. And we always look at molar volume of 1 mole of gas. Okay, so at STP, the molar volume of 1 mole of gas is 22.4 liters. This is also used in stoichiometric calculations. So 1 mole of helium at 22.4 liters is quite light. However, calcium or chloride 2, still 1 mole of gas is 22.4 liters. It's just heavier. Now, you're going to see this little picture down here. It's sort of like me saying 6 of one, half dozen of another. You're going to see it's 28.2, no matter which way we look at it. It's still going to be 22.4 liters, which equals 1 mole, which equals 6.02 times 10 to the 23rd particle. Same thing every way, which way you look at it, 6 of one, half dozen of another. Now, sample problem. We have carbon dioxide plus lithium hydroxide yields lithium carbon trioxide plus water. Now, how many grams of lithium oxide are required to remove 500 liters of carbon dioxide gas at 101 kPa and 25 degrees Celsius? Now, we need to use that molar volume to find the numbers of moles. We must convert to STP. So we're adding some steps here because it has to be STP. So we have to convert all this P1V1 P1V1 over T1 equals P2V2 over T2. So we have to convert all there. Put this in your listening check journal. Thank you. And that will be the end of your chapter. Thank you for visiting with us.